Okay, so today we're going to a bit back in time. We're leaving gravity and we're going back into the weird world of the quantum to finish something off that we sort of didn't really look at last year because it made sense to keep talking about space. And that is a concept of wave-particle duality. And so just to kind of introduce this idea and what it is and take you through a couple of examples, I want a bit of a reminder of essentially what we had the last time we were sort of looking at this topic of quantum physics. So in like the sort of the ancient times, no, sort of around the time around about sort of 1900-ish. Okay, so 1900s, there are some queries about the nature of light. Okay, what is it? How does it behave? And the problems that we've got is we have experiments such as the interference of waves through a diffraction grating. Okay, interference of light through a diffraction grating clearly says it's a wave. So interference strongly implies waves, and we have the sort of equations where if you've got a double slit, you've got lambda equals ax over d. If you've got an entire diffraction grating, you've got n lambda equals d sine theta. And this conclusively says, yeah, light must be a wave. The problem then turns up, which is the photoelectric effect, which will be solved by Einstein, because the photoelectric effect clearly indicates that light is a particle. So clearly says that light is a particle, as there is a kind of threshold frequency above which you must have in order for a photon of light to emit an electron, because waves doesn't really explain it. So and this led to ultimately Einstein realizes that light is both a particle and a wave, and he generates his sort of relationship, which is his equation, which is that light is a series of individual photons, and the energy of a photon is equal to hf, or hc over lambda, with h being Planck's constant, which is 6.63 times 10 to the minus 34, and that is joules seconds. Now, you may hopefully remember sort of vaguely how that one sort of worked. And Einstein publishes this in 1905, so this is sort of done in 1905, and the weird sort of quantum world gets sort of spills out into everything, and this includes not just this idea of the quantization of light, that light has specific energy levels, which is what explains things like emission spectra and absorption spectra, but then you have this idea that loads of other weird things are happening at the same time. There's the discovery of radioactivity, the discovery of X-rays in the late 1890s. All these things are going on, and physicists are getting a real glimpse of just how weird the world is. And then at that point, in 1924, I believe, this guy, Louis de Broglie. And Louis de Broglie has an idea, and it's a perfectly reasonable suggestion, because he knows that Einstein has basically said that it is perfectly reasonable for light to sometimes behave like particles and sometimes to behave like waves. He says that's perfectly reasonable. But why is light special? Is what de Broglie thought. Maybe actually it's slightly more fundamental that in reality, you can get particles can also sometimes behave as waves. What about things like electrons or protons or people? What physics often works in this idea of symmetry. So if you can get waves such as light behaving like particles, why can't you get particles behaving like waves. And so he sort of simplified this into an idea of what he called, he decided to basically set out a theory on the wave nature of particles. Or, well, actually, I guess at that time it would have been a hypothesis, because he did not have any experimental evidence for it. He comes up with a thought process using Einstein's logic, using the equations that Einstein built, and ends up with an idea that that for a particle that's moving through space, so a particle of mass m that's moving through space with a velocity v, should have associated with it a sort of a wave nature that has, it's called the de Broglie wavelength, and that should be h over mv, or lambda is equal to h over p. Now this wavelength, I put it in a box because it's going to turn out to be true, ends up being called the de Broglie, it's called the de Broglie wavelength. And this was so weird. He proposes this in his doctoral thesis in 1924, is I think the year he does it. And because of what he's using, and because of how he's making his logical argument, his supervisor, oh sorry, not his visitor, his examiner for his viva turns out to be Albert Einstein, because he's using all these new theories that are Einstein's. It's Einstein who at some point checks his work and says, yeah, this is at the very least plausible. There's no logical error here. He's not made an error. He's not misunderstood my equations of, like, you know, how quantum physics as we understand it works. There's nothing that says it can't be true. And so, hooray, de Broglie becomes quite happy. But you need evidence for it. You can't just sit there and go, oh, well, I've got a nice theory. You need actual evidence for it. And that evidence actually turns up really quickly, because this is the kind of time where things turn up very, very, very rapidly. And two experiments that are done in 1926. Two experiments take place, that observe the wave nature of electrons. Now, what wave nature do they observe? Well, they observe interference. That's the key. Because remember, interference is something that can't be explained by particles. You can't have two particles arrive somewhere and then start banging on about phase difference. That doesn't make sense if you're dealing with a cricket ball. So it shouldn't make sense if you're dealing with an electron. But what we had here was two experiments, both done in 1926. The top one, the Davison-Gerner experiment, bit by accident because they were trying to clean something. And they noticed that when they, so that top one, they fired an electron at a target and were looking at reflection. And their idea was that this reflection should be diffuse. So electrons should just sort of go in a lot of different directions, because at a level of an electron, it's impossible to make a mirror smooth enough. But what they found as they moved their detector around is they found that there were certain angles where they would get lots of electrons coming back and some angles where they wouldn't. They're basically observing maximas and minimas, which is only something you can see if you're dealing with waves. The second experiment, which was actually setting out to do it, was George Thomson, and he basically did the equivalent of using a diffraction grating. But what he used was a thin piece of foil, and he built a diffraction grating actually using the interatomic spacing between the gold atoms. So what we end up having in this sort of George Thomson experiment, you have sort of a beam of electrons, and what they're seeing is a diffraction grating essentially made out of atoms. And because it's not very thick, you know, it's okay, it doesn't make too much difference. And so as the electrons travel through, what we end up seeing is some sort of diffraction pathways. Now you'll notice that this is a circular diagram, and that's because we're seeing this in it gets done in 3 dimensions, because you've got a 3-dimensional diffraction grating, and you will have some discordance between different layers. So when you look at the layers of the sort of, that's one of the things about metals, is that you don't necessarily have all the layers like nicely arranged like this. So you might, your next layer might be here. And so what you end up with is diffraction in lots of different directions, and you'll get things coming out and around the side. And you end up with this circular diffraction pattern. And I think, you know, what I meant to put in is I might put in an actual copy of this. So okay, so they come out looking like this. Actually, I'm gonna see, they come out looking like this. So what we see is, we see very clearly we've got a central maxima, and then we've got these rings. Some are very much brighter, but this is something that is not explicable if you think of electrons solely as particles. In order to do this, you've got to have electrons behaving at points like waves. And so this is it in action. So you've got, this is electron. And because of experiments by a guy called Bragg with X-rays, they were able to observe 2 things. One is that actually you can see very similar patterns if you fire X-rays at a thing. I'm trying to see if I can find a pattern of. I'm trying to see if I can find one, but I am not seeing one immediately. 2 things. Oh well, there's a very okay. So copy image. Right. So this is a 10 microsecond X-ray exposure, and you've got on a crystal, so a similar-ish kind of idea, and you get this sort of circle of maximas. This time it's a very short exposure, and also it's much neater because with X-rays you're able to much better control the sort of the energy of the X-rays. So you can be much more selective with things. So this is, you know, that's an X-ray diffraction pattern through a crystal, and on the top is an electron diffraction pattern through a crystal. And you're able to observe in many cases that their wavelengths are very similar, and their wavelengths are very similar because they're essentially being split up. They're seeing a grating with basically the spacing between the sort of the grating spacing is essentially basically the width of an atom, or the diameter of an atom, which is quite fun. So this wonderful property, it led to 2 things. First, it led to these guys getting a Nobel Prize in 1927. These guys win. It's quite funny that George Thomson wins a Nobel Prize for doing an experiment to show that electrons are waves, because his father got a Nobel Prize for showing that they were particles, which is quite fun. And Louis de Broglie would get his Nobel Prize in 1929. Which is not bad. 5 years out of his PhD thesis. Pretty awesome. So this means that what we can do is, this is what allows us with electrons to start probing the nature of matter, because we can control electrons and we can swing them around quite nicely. So you know, we can make a thing called the electron gun. So we can do a thing called electron diffraction experiments. So in order to do this, it's quite nice because it builds together a few different things. We have to basically build it into sort of 2 parts. The first part of our experiment is building a thing called an electron gun. And then we have a target and we fire it at a screen, which will glow like when as electrons strike bits of it. And so what we've got is an electron gun bit, and then we essentially have a diffraction part to the problem. And this is nice because this first bit you can solve using sort of that comes out from your knowledge of like, you know, circuits and things. And the second bit is something that comes out of knowledge of waves. So it's a nice sort of weirdly synoptic thing that can exist within that, in that part of the paper is this idea of two things. So how do you build an electron gun? An electron gun, it's quite nice. You get really using different colours. We need a coil of wire. And what will happen is this coil of wire will get hot, and you get at this thing a thing called a thermionic emission. So that means that you eject electrons from the coil of wire because the coil of wire is hot. Now, so what that will mean is that you'll get an electron that will just sort of spit out into thin air. I need to move things down a bit because I've decided, because I've not done this particularly well. You can move down, and you can move down. We need to accelerate them. How do we accelerate them? Well, we stick a plate. Stick a big positive plate, but with a hole. And that will be up to potentially several thousand kilovolts. And then what will happen is we get our electrons. I'm going to colour my electrons slightly differently now because I am a bit. Let's go with a blue electron. Our electrons will screen through. Now, some of them will hit the plate, but others will go straight through because that's a completely straight line. And they will gain a kinetic energy as they go across this potential difference. So as they go across this potential difference, they gain a kinetic energy. We'll deal with that in a moment. They will then strike the target, which is a sort of a thin slice, thin atomic slice, and we will then get diffraction at various angles. So we'll get a central maxima 0, 1, 2, 2. Okay, so we get our maximas, and they will be at some angle theta. So by what we can do is by measuring the angle between two things. Okay, so what we can do is by doing we can use n lambda equals d sine theta. We can measure this angle, and we can do one of two things. Now, Thomson knew what d was, so he knew what d was, and was therefore able to calculate what lambda was, and he was then able to go and predict what lambda should be given de Broglie's prediction, and found that they agreed. But if you're going to probe something that's completely new, you can know your lambda by doing something over here, get your angle, and you can measure the intraatomic spacing of the thing that you just invented, which is kind of clever. So let's take, let's take this sort of through. So let's say that we have a angle to our first. Let's just go to our first one. Let's give it some numbers. Let's say that angle is 12 degrees. Okay, and let's say we've accelerated this to 4,000 volts. Okay, let's give that a kind of a, how do we work out, say, the intraatomic spacing? What is d using kind of like this in de Broglie's equation? So step 1. So electrons are emitted from the coil and are accelerated across a potential difference of 4,000 volts. Now, what does this mean we can then do? Well, we can say they therefore gain energy So energy is equal to work done. Work done on a charge as it comes through, energy equals QV. So Q is going to be the charge on an electron, 1.6 times 10 to the minus 19. V is 4,000. So, I mean, in terms of electron volts, this is 4,000 electron volts, but we'll work it out into joules. And joules are, so we've got 4,000 times 1.6 times 19, 6.4 times 10 to the minus 16. Okay. So that's a nice thing about if you know the potential you've accelerated them over, that's brilliant. Okay, so we can then use, this is such a lovely situation, so we can then use, as the kinetic energy equals a half mv squared, which will also equal 6.4 times 10 to the minus 16, we can find the velocity of the electron, as the mass of an electron is 9.11 times 10 to the minus 31 kilograms. So we can throw that in. So we can say, oh, okay, we've got our numbers. So that means that V is equal to 2ke over m square rooted. That's a terrible square root, sorry. Times 2 over 9.11 minus 31. So I square root that answer, and I get 3.75 times 10 to the 7, which is great. Oh, it's good. It's less than the speed of light. Happy. Excellent. About 10% of the speed of light. It's easy enough to do. Right. Okay. We can then use de Broglie. The de Broglie wavelength is lambda equals h over mv. I mean, it's a long and tortured one, so we get 6.63 times 10 to the minus 34 over 9.11 times 10 to the minus 31 over times 3.75 times 10 to the 7. So 4 over 9.1 to the minus 31, 3.75 e to the 7. Right, okay. And what we get here is about 1.9 times 10 to the minus 11. Okay, so this is, around about 220 or 200. No, not 200. Sorry. So you're getting there about 2 times 10 to the minus 11. So we're looking for then picometers, about 20 picometers. 20. So it's tiny. So which is, roughly on the order of the size of an atom, which is great. We can then say, okay, we can then get to use the diffraction gradient equation. So move that so completely at the top. Diffraction. Okay, we've got theta is equal to, we've measured it being about 12 degrees. So we've got n lambda is equal to d sine theta. So we've gone for n is just 1. Lambda is 2 times 10 to the minus 11. And sine theta is obviously sine of 12. So we've got d is 2 times 10 to minus 11 over sine of 12. And for that, I get about 9 times 10 to the minus 11 meters, or around about 10 times 10 to the minus 10. So it's about 10 to the minus 10 meters, which is roughly the size of an atom. And I've forgotten the name of it. There's a word which is for that, and this escapes my mind. And that's kind of how this thing can. This is what they did. They were able to do this. Now they started with what they started off doing was sort of sections 1, 2, and 3. To get a prediction for the de Broglie wavelength using de Broglie's logic, and then they fired it at things they knew from studying them with X-rays, and said, "Oh, look, they agree. They're in agreement with what they are." And so this is what we end up with. It's the de Broglie wavelength. So that's kind of nice. So the wave nature of any particle is lambda h over mv. And the thing is what we need to do is that one thing that's nice is this is kind of why we can get electron microscopes, because we can fire electrons at things. We will find that the electrons will be diffracted, we'll get an interference pattern, and we can compute, therefore, what it's gone through. And by altering this potential difference here, if we increase it, the electrons are going faster. And if they're going faster, well, that wasn't what I meant to do. If they are going faster, then if we look here, then what will happen is that our wavelength will go down, which means that we'll be interested in smaller things, and we'll be interested in smaller gaps that we can start sort of probing and trying to find out what their nature is. Similarly, if we've got more massive particles, say a neutron going at a neutron traveling at a certain velocity, the same as an electron, will have a wave nature which is 2,000 times smaller, which means you can probe smaller bits of matter. You can just probe this. But why don't we see this on our level? Well, the problem is that we just aren't, because h is such a small number. We can never really get to a stage where we can observe this in the real sort of world. So if we can, if we did an example, if we considered a cricket ball of, let's say, I now need to look at the mass of a cricket ball because I don't know it's on my head. So 160 grams, and fastest cricket delivery in meters per second, hopefully 161 kilometers per hour. That's not terribly helpful. So we've got 0.16 kilograms delivered at, what did I just say it was? 160 kilometers per hour. So 160 over 3.6, I believe it is. So delivered at 45 meters per second. Has an effective wavelength of, so we've got 6.63 e to the minus 34 over 0.16 over 45, and we end up with that gives us that lambda, the Broglie wavelength, is 9.2 times 10 to the minus 35 meters, which is fundamentally too small to notice. We need to be dealing with things that are very, very, very tiny in order to detect the wave nature of them. But with electrons, we do. And it is as quantum physics has evolved and as people have thought about different things with quantum theory, this electron, this wave nature of particles, is what we think is going on when you get all the way down to the things that happen on the quantum level. Say, for example, when you've got things dealing with, say, the decay, radioactive decay, is fundamentally in some way controlled by wavelengths and the wave nature of things, because waves give us probabilities, not certainties. And even things such as, when fusion can occur in a star, well, if you do the calculations and you treat these particles classically, they should never, two hydrogen atoms, even in the core of the sun, should never fuse together. But what they've realized eventually is that, so if you had two particles sort of going at each other, they just wouldn't get close enough together before they zoom off. But if you treat them kind of as waves, well, they're wave things, they're wave natures. That is what's able to get close enough. And in order for fusion, you just kind of need to go to things with this kind of wave nature starts to overlap. And that's the thing, once they overlap, gives you a chance, a possibility of generating fusion and turning this first step and turning into deuterium and other things. So everything at that length starts to happen really as waves. But mathematically, it's fairly nice, it's fairly simple, it's very straightforward. I hope it's kind of made sort of sense. I know there's been this thing that's been sitting there for a long time and we haven't done it yet, but here we go. That is the electron. So that is the diffraction of electrons. You, of course, as per normal, you don't need to know any of this history stuff. You just kind of need to know the equation, and there's this worked example here, as you got.